and welcome all of you to this session of Applied Thermodynamics. Today we shall discuss about the concepts of second law of thermodynamics. In the previous lectures, we have seen that first law of thermodynamics states that energy is always conserved. So for a control mass system or a control volume system, it is quite surely understood that it is quite obvious that energy is always conserved. That means the energy which is entering the control mass or the control volume system, that is exactly equal to the energy which is leaving the control mass or the control volume system. Now the question which is to be asked is that what happens if the process itself is not feasible? So thermodynamics, the first law of thermodynamics doesn't have any answers to this question. It is only used to uh, to understand. It is only used to understand the conservation principles of energy. Okay, but it doesn't give us any kind of information regarding the probability or the feasibility of the process itself. Here now you can see some writings over the screen. The first law of thermodynamics states that a certain energy balance will hold when a system undergoes a change of state or a thermodynamic process. Okay, so this is well understood here, but it does not give any information on whether the change of state or the process is at all feasible or not. So you if you don't have the information about the feasibility of that process, you can't do the energy balance. So this question is answered by second law of thermodynamics. So a process which is feasible or not, it is a very important question. Suppose you are trying to create some design which involves some thermodynamic processes, but you don't know the information about the occurrence or the probability of that process. Okay, it is at all possible or not, you don't know that. So then you can't move with the design, you can't move forward with that design, so you need to change that. So if you don't have proper understanding about the second law, which is the most important axiom of the physical sciences, if you don't have proper understanding about this law, then you can't move forward. Okay, so here an example is provided here. The first law cannot indicate whether a metallic bar of uniform temperature can spontaneously become warmer at one end and cooler at the other. Okay, so that means it is a process. Okay, it can be a hypothetical process. A plate, a metallic bar is maintained at an uniform temperature. Now someone proposes that this metallic bar needs to be warmer at its one end and cooler at the other one. So this involves a thermodynamic process, but first law can't answer this question. First law doesn't have any answer to this question. So to solve this question, to understand the possibility of the occurrence of a process, to understand the feasibility of a thermodynamic process, we need to study second law of thermodynamics. So let us start with that. So before that, we need to understand what are the different types of thermodynamic processes which we can see. Okay, so uh, before starting the discussion on the thermodynamic processes, I would like to introduce you the concept or the principles of directional constants which are already involved with the natural processes. That means in all possible natural processes, there is a inbuilt directional constant. Like water always flows from higher elevation to lower elevation. Heat always flows from higher temperature to lower temperature. Mass diffusion. Mass diffusion always takes place from the higher concentration to the lower concentration. Okay, so here you can see a directional constant which is always incorporated over here. Okay, this type of processes are called as spontaneous processes. Spontaneous or natural processes, whatever you may say, but they have a directional constraint always incorporated within it. That means you can change the direction of the process, but you can't specify that process as a natural one. So that means any spontaneous process have a natural directional constant within it. That means it can occur in a single direction only, but we have to understand that we are talking about the spontaneous process. So to keep the process as a spontaneous one, we need to understand that the directional constants are always implied on that. That means what I have given you examples, like water flowing from higher elevation to lower elevation is the opposite of this. That means water will flow from lower elevation to higher elevation. Is it not possible? Yes, it is possible, but the possibility depends on the external agency which we are applying by ourselves. So if we don't apply some external force to take the water, to move the water from the lower elevation to the higher elevation, water will not move from the lower elevation to the higher elevation spontaneously or naturally. We have to provide some external effect. Okay, so that means spontaneous processes always involve a directional constraint within it. Now, what happens if you take this discussion a little further and let us consider some different thermodynamic processes where we are always implying an external agency. That means we are talking about those processes where the process itself is occurring by the help of some external effects. Like suppose we take an example of electrical current which is passing through an wire. Remember that this wire is insulated. Then what will happen? Heat will generate, and we will understand, we will find that there is a rise in the temperature. Okay, but let us consider the opposite of this process. So what we will do? We will cool this wire. So is it possible that the electrical energy or the electrical work will regenerate? It is not. It is not going to happen. That means cooling the wire will not help us to generate the electricity. That means the opposite of the process is not going to happen. So there will be some unidirectional processes which is occurring with the application of external aid, but still they are they can be occur they can occur in a single direction only. The opposite of these thermodynamic processes cannot occur. That means in nature you will find uh, there are possible there are three different type of processes possible. Okay, so if we uh, consider the directional constraints involved in it. Okay, so keeping the directional constraints in our mind, we can divide these processes in three separate categories. So this is the first one, the spontaneous natural processes, like water flowing from the higher elevation to the lower elevation spontaneously. Like this one, when we are considering electricity is flowing through a wire, the wire is insulated and we observe temperature rise. Okay, and heat generation there, or thermal energy generation. Okay, heat generation is not the correct word. We will use thermal energy generation. So, but the opposite of this process is not possible. So, uh, uh, we can understand that there there are always directional constraints involved in all possible thermodynamic processes. Okay, now moving on to the processes which are possible in both the directions. Like suppose you are heating a body from a lower temperature to a higher temperature. Okay, then you wish to um, keep this body at the same initial temperature. Then what will do? You will just cool the body. You will cool the body from the higher temperature to the lower. So after cooling the body, the system will reach the same initial temperature. But the most important thing you must understand is that the surroundings will suffer a permanent damage. That means the surroundings, the states or the thermodynamic conditions of the surroundings will be permanently disturbed. Now you may ask, if the system is reaching its initial state, then why the surroundings is not reaching the initial state? Okay, so this question is a very valid question, and this question can be answered by understanding the concepts of irreversibilities present within the system, or irreversibilities which occur during the thermodynamic process. So we shall not discuss about these irreversibilities just now, but we'll keep it for our discussion. So but what I was trying to say that there are processes which are possible in both the directions. So what the main motto of this discussion is that there are processes which always occurs in a single fixed direction. Okay, there are this type of processes which are occurring in a single fixed direction. They can be spontaneous, or they can be uh, they can be done with the help of external effects. Okay, now these spontaneous processes can be also reversed, but if you want to reverse it, then you need to apply some external force. Now here you will see there are some natural processes which are occurring in both the directions, so they can occur in both the possible directions. But in that case, what is happening, though the system is reaching its initial state, the surroundings is not. Okay, so similarly, if we discuss about the processes which is possible in both the directions, we must say that heat engines and heat pumps are those devices which are occurring, which helps us to understand the concepts of processes occurring in both the directions. What does a heat engine do? Heat engine delivers work. And how does it deliver work? It takes heat from a high temperature body and it performs some work and rejects heat to a low temperature body. So this is the mechanism by which a heat engine performs work. So the main motto of this, what I am trying to say is that the heat engine is taking heat from a high temperature body and rejecting some other heat to a low temperature body. Okay, now comes the heat pump. What does the heat pump do? The heat pump takes heat from the low temperature body and it rejects the heat to the high temperature bodies. And in this case, you need some external work. Until and unless you don't provide an external work, the heat pump will not work. Okay, so these are the examples of the different thermodynamic processes which can occur. And in all of these cases, there are some inbuilt directional constraints. So this process can occur in this single direction. And if we need the opposite one, then there will be some directional constraints involved in it. So, like if we discuss about the spontaneous processes, then we'll see we always need an external effect to make possible the opposite of the spontaneous processes. So if our wish is to make happen the opposite of the spontaneous processes, then we need to provide an external effect. Now here the processes which are possible, which can occur in the two possible directions. In that case, you'll see the surroundings is getting permanently disturbed. So this is the directional constraint involved here. Whatever you do, the processes will uh, afterwards, whatever you do, the surroundings will get disturbed. So no one can't change it. This is going to happen. Okay, So this is the directional constant concept which I would like to mention. Now, after this discussion, we shall move on to understand the qualitative difference between heat and work. So let us see that. So now we will discuss about the qualitative differences between heat and work. Okay, so here you can see that we have considered two separate systems where we have provided heat input to the system. You know, heat and work, they are both the forms of energy in transit, so they can cross the boundary of the system. So from the surroundings, heat input of Q12 has been given to this system. So because of this heat input, the states of the system change, and because of this changing state, a thermodynamic process is occurring. Now after this, a thermodynamic cycle is completed via the work output. Okay, so for the process 1 to 2, you can see there is a heat input here, and for the process 2 to 1, there is a work output. Okay, now the understanding which we need to make from this case is that this Q1 to 2 is always greater than W1 to 2. That means the heat input which we have provided here is always greater than that of the work output. That means the heat which we have provided, that is not completely getting converted into work output. So the heat input is not completely converted into work output. Okay, so there is always heat rejection. So that means, let us assume we have provided 100 joules of heat. Now since this Q1 to 2 will be always greater than W1 to 2, let us assume 90 joules 90 joules of work output we have found. Now the rest of the 10 joules will be rejected. Okay, so this is the heat rejection which we are talking about. And in all thermodynamic processes where heat is the input, in that case heat cannot be completely converted into work. Some amount of heat will always be rejected. So this needs to be understood clear cut. Okay, so this needs to be uh, properly understood, that the heat cannot be completely converted into work. There will be always some amount of heat rejection. Okay, but in case of work, when work is considered as the input, there is enough provision, or it is absolutely correct that the work can be completely converted into heat. So there is no prohibition regarding that. So if you provide 100 joules of work input, this 100 joules of work can be completely converted into heat. Okay, so this is the understanding. So this is the basic difference between heat and work. One energy is completely converted into the another one. That means work can be completely converted into heat, whereas heat cannot be completely converted into work. It means that energies can be categorized from this perspective. That there will be some kind of energies which can be completely converted into a separate form, and there will be some kind of energies which can't be converted. So the energies which is completely converted into the another one, example is work, which is getting converted into heat completely, this type of energies are called as high grade energies. Whereas heat which is not getting completely converted into work, they are termed as low grade energies. Okay, so energy have this certain gradation depending on the convertibility or the interchangeability. Okay, so this is what I was trying to say. I hope you have understood this, and we'll be discussing about this high grade and low grade energies in a much detailed fashion when we'll be discussing about the availability principles or the exergy principles. But this is for your information and this will help you. The basic understanding is that whenever there is heat input, there always will be some amount of heat rejection. And with this understanding, let us take a So let us discuss about heat engines. Now, heat engine is a device where the system operates in a cyclic process to produce work when there is some heat input to the system or the to the engine. So heat engine, what does it do? It receives heat from the high temperature source, performs work, and rejects heat to the low temperature process. So let us draw a cycle here. So let us consider a engine which is working in a cyclic process. So what does it do? It takes heat, right? So it is taking heat. It is taking heat and it is providing work. Now, how do you supply heat? So to supply heat, the engine needs to be in contact with a high temperature body or a high temperature system. Now we'll discuss about these high temperature systems later on, but let us discuss the mechanisms of the heat engines. So how does a heat engine work? It takes heat. It takes heat from a high temperature reservoir and it gives some work output, and the rest of the heat is again rejected to a low temperature sink. Okay, so I think we have understood. So here heat addition is taking place. Okay, so whenever heat addition is taking place, it means that this heat engine should be in contact with a high temperature reservoir. Okay, so let us assume the temperature of this um, high temperature reservoir is T1K. Let us call this reservoir as source. Okay, let us call this as source, and this is the low temperature reservoir where heat is rejected. So let us take this heat addition as Q1 and let us take this heat rejection is as Q2, and here is your low temperature reservoir which we call as sink. Okay, so what are the specialties of this thermal energy reservoirs? So these two, the source and sink, they are called as thermal energy reservoirs. Okay, so what are the specifications of these thermal energy reservoirs? They have infinite heat capacity. Okay, so they have infinite heat capacity. That means after a certain amount of heat transfer, the temperature doesn't change. It remains as it was earlier. Okay, so infinite heat capacity. So we can take the examples of boilers or high temperature furnaces where the temperature remains constant. Okay, so boilers can be taken as boilers can be taken as the example of sources or the high temperature reservoirs from which heat is rejected to the engines to perform some work, and after that the temperature remains constant. So there is no change in the temperature. Okay, so they have infinite heat capacity. And here for the sinks, when heat is rejected to the sinks, let us assume we can take atmosphere or the a large river as the sink. You will see that if we add heat, so here you can see that this Q2 heat is being added to this low temperature reservoir. So addition of this heat. Okay, so I would like to say that this heat is the rejected heat by this engine, and this heat is being added to the sink. Now the heat which is added to the sink does not change the temperature of the sink. Okay, So whenever heat is added to the sink or the low temperature reservoir, you will see that the temperature of the sink doesn't change. It remains invariant. Okay. Now, so the basic understanding is that, so I have said you earlier that, say, whenever there is heat input and it is providing some amount of work, there should be always some amount of heat rejection, that is Q2. So this is the heat addition and this is the heat rejection. Now if we perform the energy balance, then what will be? You had Q1 as your heat input. Okay, now you received work and there was some heat Q2 which got rejected. So this is your energy balance. Now let us consider in eta T as the thermal efficiency. So efficiency is the measure of the effectiveness of the heat engine by which it can perform work after it has been fed some amount of heat. Okay, so efficiency, it is a term, it is a ratio between the output and the input. So obviously you are receiving work as your output here and heat is your input. So this is the added heat, that's this Q1 is the heat added and this W is the work output. So you can write thermal efficiency as output or work output divided by heat input, that is Q1. So this is your eta. It denotes the thermal efficiency of a heat engine and it can be written by this formula. Now since you know that Q2 this Q2 can never be zero, because there should be always some amount of heat rejection. So this Q2 cannot be zero. If this Q2 can't be zero, then this thermal efficiency of the heat engine can never be equal to 100%. Okay, so you have to remember that in ideal conditions, so if we take ideal conditions, means there is no energy loss, there is no dissipative effect. Okay, so there are no frictional losses or no energy losses because of the dissipative effects. Still, at those ideal cases, the efficiency of heat engine can never be 100%. So this is a certain directional constant which we were talking earlier. This is also implied here. These heat engines can't have an efficiency of 100% in the ideal cases also. Okay, I hope you have understood it. In the ideal cases, the heat engine can never have an uh, can never have an efficiency of 100%. Okay, so this is a very important question. You will see that many you will be asked in the interviews or many vivas. But the basic understanding is that since this Q2, this heat rejection is always greater than zero, it suggests that this uh, this efficiency, this eta T, or the efficiency of the heat engine will never be equal to 100%. Okay, so I think you have understood this concept. Now from this understanding, let us see the Kelvin Planck statement of the heating of the second law of thermodynamics. Second law of thermodynamics. Okay, so we'll be moving on to the discussions of the second law of thermodynamics and the Kelvin Planck statement. Okay, so here you can see the Kelvin Planck statement. It is impossible for a heat engine to produce net work in a complete cycle if it exchanges heat only with a single fixed temperatures. Okay, so if we draw a heat engine, it will help you to understand in a much better way. So let us take this as the source, which is maintained at a temperature T1, and it is taking heat Q1 from the uh, So this is your heat engine here. So this is your heat engine here, and you see that this Q2 is equal to 0. Okay, so this is your W net. So here this W net becomes equal to the heat input, that is Q1. Now I have told you earlier that this heat rejection can never be 0. That means it is impossible for a heat engine to produce net work in a complete cycle if it is exchanging heat only with bodies at single fixed temperature. Here, by the statement with bodies at single fixed temperature means that it is talking about the source. If the heat engine only interacts with the source, uh, then it can't produce continuous work output. Okay, because there has to be some amount of heat rejection always, and to reject this heat there should be another body present with different temperature. That means a sink should be always present. So whenever you will see that there is no sink present, it doesn't accomplish that this engine can produce continuous work output. Okay, so this is a very important statement of second law. So with this understanding, let us deal with a hypothetical concept which we call as perpetual motion machine. So the diagram which I have shown you just a few minutes earlier, it is same. So this is your heat engine. So just I will draw it in a much better way, I promise that. Okay, so this is heat engine. Now this is your source which is maintained at a T1 temperature. The absolute temperature is T1 Kelvin. It is receiving heat Q1 and it is rejecting nothing. That means this Q2 is 0. So which we have just now discarded, which is not at all possible according to the Kelvin Planck principle that is now discussed here. That means here you can see a hypothetical machine, a perpetual motion machine 2, which is interacting with the source only. That means it is interacting with the single fixed temperature and it is providing continuous work output. Or in other words, here you can see a heat engine which is 100% efficient. Okay, so these two statements, like the engine is 100% efficient and it is only interacting with the source, these two statements are violating the Kelvin Planck statement of second law of thermodynamics. So this perpetual motion machine 2, we have already seen the perpetual motion machine 1 in case of first law of thermodynamics. Okay, so here from this understanding we can easily sense that this perpetual motion machine 2 cannot be practically done. It cannot be designed in the practical cases. So there is there is nothing to discuss about this 100% efficiency. Heat engine can't never obtain 100% efficiency. Okay, so there is okay, so with this let us see the reverse case of heat engine. So in case of heat engines, we have seen that it is taking heat from a high temperature reservoir and it is rejecting heat to the low temperature reservoir, and within that it is giving some work output, right? So if you remember that heat engine always takes heat from the high temperature reservoir and provides some work output, and after that some amount of heat is rejected. This is the basic mechanism by which a heat engine works. Now let us take the opposite of the heat engines. Okay, so let us discuss what do we mean by heat pumps or refrigerators. So this is your source. This is a general consideration that we take the source as T1 temperature and the sink is at T2 temperature. Since the source and sink, they are infinite, they have infinite capacities, infinite thermal capacities, their temperature doesn't change. So now let us do the opposite of heat engine. That means heat engine was receiving from heat engine was receiving heat from this high temperature source, right? Here the heat pump will receive heat from this low temperature sink, okay, and it will it will reject heat to the high temperature source. Now you know that heat can't flow from the low temperature to the high temperature. Obviously this T1 is greater than T2. If I haven't mentioned this T1 greater than T2 in the case of heat engines, please check it and correct it, because this, if T1 is not greater than T2, then this heat engine or heat pump will not work, okay. So it is already given, okay, it is a perfect assumption. So now let us move on to the discussions of heat pump. So heat pump takes heat from a low temperature reservoir which is maintained at T2 Kelvin, and it rejects heat to the high temperature source which is maintained at T1 Kelvin. Now this is exactly opposite to the spontaneous process. That means heat can't spontaneously flow from the low temperature to the high temperature. So you are trying to act against the nature. So how you can do it? You need to put some external effect. Now what do you mean by this external effect? We are talking of work input to the heat pump. So until and unless you don't provide this external work input to the heat pump will not be able to transfer this heat from the low temperature reservoir to the high temperature reservoir. Okay, so let us take this heat which is transferred as Q2 and Q1. Okay, so if we perform the energy balance, you will see this W is your input, it is your work input, and this is Q2. Okay, so this is Q2, which will be equal to Q1. Okay, so this is the basic energy balance which we have seen here. Here W is the work input, so that heat pump can transfer this heat, this low temperature heat. uh, so here you can see that there is work input to the heat pump, so that the heat pump can transfer this Q2 heat from the low temperature reservoir to the high temperature reservoir. So you might be suffering some sound disturbances. Please ignore that. I hope it will be corrected soon. So let us concentrate on this point. So this is your energy balance. This W and Q2 were your energy inputs, and this Q1 is your energy output, right? So how do we measure the performance of a heat pump? Okay, so let us see that. So to measure the performance of a heat pump, we define a term COP. COP is called as the coefficient of performance. Okay, so COP is defined by the ratio of desired, uh, it is your desired output divided by work input. Okay, so desired output divided by work input. Now what is your desired output here? Your desired output is that you need to transfer this Q2 heat, and uh, for that purpose W work is given to you as your input, and afterwards, finally you'll see that this Q1 heat, this high temperature heat Q1 is rejected to the high temperature source. Okay, so your desired effect, now remember that uh, according to your desire, sometimes we are concerned about the high temperature heat. That means we are concerned about this Q1. In that case, the device will be called as heat pump. And when we are concerned about this low temperature heat, this is your low temperature heat, then this device will be called as refrigerator. Okay, so this heat pump is then called when it is we are concerned about the high temperature heat. Okay, that means you need to keep your room cool, your surroundings is at a lower temperature. So what will happen? Heat will flow from your room to the surroundings. So heat is going to flow from your room at a certain fixed rate to the surroundings. Now you will provide some external heat input to your room so that it balances the heat which is going outwards. Okay, so here comes the importance of a heat pump. By the help of heat pump, you can transfer this heat to in your room so that it balances exactly to the heat which is going out to the surroundings. Okay, so but in case of refrigerators, it is exactly opposite. That means you need to keep your room cooler than the surroundings. So the surroundings is at higher temperature, and you wish that your room should be maintained at a lower temperature. So by virtue of temperature difference, a natural heat transfer process will occur. That means heat from the surroundings will flow to your room. So this heat transfer will take place at a certain fixed rate. Now, if we employ a certain device which will always take back this heat to the surrounding, which will always deliver this heat outside of your room, then we are concerned about this low temperature heat. And at that moment, this device will be called as refrigerator. So this is a sharp classification you must understand. So heat pump is always concerned about this high temperature heat, whereas refrigerators are concerned about this low temperature heat. So while defining this COP, if we define the COP of a heat pump, then it will be defined as Q1 divided by W. Okay, so it will be always Q1 minus Q1 by W, that is Q1 minus Q2. So this W is equal to Q1 minus Q2. This is very simple. Now what will be the COP of refrigerator? In case of refrigerator, what is your desired output effect? Your desire is essentially concerned about this low temperature heat. That means this Q2. So you are concerned about this Q2, right? So this Q2 divided by Q1 minus Q2. Okay, so by simple mathematics you can understand that suppose you have this Q1 divided by Q1 minus Q2 is your COP for heat pump, right? So this is your okay. So let us do a little bit of mathematical operations here. Let us add and subtract Q2 from the from this term. Okay, so we are subtracting Q2 as well as adding up, so the ultimate result is 0. Now if we divide this, if we take the fractions, then it would be Q1 minus Q2 divided by Q1 minus Q2, so it is nothing but 1. Okay, so 1 plus it will be Q2 divided by Q1 minus Q2. So which term it was? It was Q1 divided by Q1 minus Q2. Q2, that was COP for heat pump, right? We change this term into 1 plus COP, so we can write 1 plus COP of refrigerator. So this is a very important formula. I think you have understood it. So this is a very simple mathematical operation. By adding up Q2 and subtracting the same Q2, we can divide this equation, we can distribute this equation into 1 plus Q2 by Q1 minus Q2, which represents, we know that this Q2 by Q1 minus Q2 is nothing but the COP of the refrigerator. So this formula can be simply generated. Okay, COP of heat pump is equal to 1 plus COP of refrigerators, and COP, you know, it is the desired output divided by work input. In case of heat pumps, we are concerned about the high temperature heat, whereas in case of refrigerators, we are concerned about the low temperature heat. Okay, I hope you have understood the concept of heat pump and refrigerators. So the basic fundamentals from where we started this discussion was that it is operating exactly with the opposite of heat engine, right? Heat engine takes heat from a high temperature source, delivers work, and rejects heat to the low temperature sink. What does heat pump do? Heat pump takes heat from the low temperature reservoir, rejects heat to the high temperature reservoir, and during this process, to make this process feasible, you need to employ some external work from the outside. Okay, so until and unless you are not providing that external work, this heat pump will not work. Okay, so I hope you have understood properly that heat engine and heat pump, they have complete different methods of operations. They are operating exactly opposite to each other. Okay, so the method applied in the cases of heat pump and heat engines, they are completely different from each other. They are exactly opposite. So with the understanding of heat pump, let us see a another important statement regarding the second law of thermodynamics, which we call as Clausius. So Rudolf Clausius and Kelvin Planck, they were the this scientist laid the foundation of second law of thermodynamics. So let us see Clausius statement of second law. Okay, so it says that it is impossible to construct a device which, operating in a cycle, will produce no other effect than the transfer of heat from a cooler body to a hotter body. That means if we try to see the diagram here, so this is your source, this is the hotter body, this is your, let us consider the heat pump. So heat pump is also a cyclic device, mind it. So here is your T2. So T1 is greater than T2, right? Now, just 1 minute. So, since T1 is T2, by virtue of temperature difference, by spontaneous processes, heat will transfer from high temperature, that is T1, to the low temperature T2. But here, regarding this Clausius statement, it is mentioned that it is impossible to construct a device which, operating in a cycle, will produce no other effect than the transfer of heat from a cooler body to hotter body. That means it is concerned about the transfer of heat from the lower temperature to the higher temperature. So this process, that means transferring of heat from the lower temperature to the higher temperature. So this is not a spontaneous process. You can only achieve this if you supply some amount of external work, right? So when you are supplying some amount of external work, that means it is obviously producing an effect to the surroundings. Okay, this work is provided by the surroundings to this system. I hope you have understood it. So I think you must have understood this Clausius statement. So you don't need to remember these statements, you need to understand. Okay, so one might say that the Kelvin-Planck statement of second law of thermodynamics and the Clausius statement of second law of thermodynamics, they are seeming to be um, different from each other, but in reality they are not at all different. They are actually the same. And how we can prove the same thing? So we will be establishing that this Clausius statement and Kelvin-Planck statement, they are absolutely equivalent to each other, and let us start the discussion on that. Okay, so let us start it. So let us first consider a heat pump. So this heat pump is violating the Clausius statement. That means it is transferring this Q1 heat from this cold reservoir or the low temperature reservoir to the high temperature reservoir without creating any external disturbances. That means it is violating the Clausius statement. Okay, so it is taking heat Q1 from the cold reservoir and it is transferring heat, this Q1 heat, to the hot reservoir without creating any kind of external effect. So it is a clear violation of Clausius statement. Now what happens here? If this Q1 heat is given to you and you can add up this Q1 heat as the input heat of this heat engine. Now what you are doing, you are connecting this heat pump and heat engine via this heat. Okay, so now you can easily understand that the rate of working of the heat engine is such that the rate of working of the heat engine is such that Q1, the heat which is discharged by this heat pump, it is being used as the it is being used as the heat input for this heat engine. Okay, and it is delivering some work. It is delivering W net work, which is equal to Q1 minus Q2. So now understand that when this heat Q1 is taken as the heat input for this engine, you can understand that the source has become redundant. That means there is no application of the source. You don't require the source now because this heat is enough to feed this heat engine. Now when, if you remember the Kelvin Planck statement, it mentioned that no heat engine can produce continuous work if it only interacts with the bodies at a single fixed temperature. So here, this heat engine is only interacting with a single fixed temperature, and that is this cold reservoir. This heat engine is not interacting with this hot reservoir. It is only interacting with this cold reservoir where it is rejecting this heat Q2, and this Q1, this heat engine is not receiving this Q1 from this hot reservoir. It is receiving this Q1 from this heat pump, right? So in this case, this heat engine has become a device which is supplying continuous work, but it is only interacting with the bodies at a single fixed temperature. Okay, so that means it is violating the Kelvin Planck statement. So it is quite obvious that if the system is starting to violate Clausius statement, then it will obviously violate Kelvin Planck statement also. So here you can see the opposite. That means you can see a heat engine which is violating the Kelvin Planck statement. That means it is clearly visible that it is only interacting with the source and there is no heat rejection. So obviously it is a violation of Kelvin Planck statement. Okay, now what happens here? Now the work which is created by this, which is generated by this heat engine is uh, is enough to feed this heat pump. Okay, now this heat pump is receiving this heat Q2 from this sink, okay, low temperature reservoir, and it is rejecting heat Q1 plus Q2. Okay, so uh, here this heat engine E and this heat pump P, they are together. They together constitute a heat pump cycle, and they are doing what they are doing. They are transferring this low temperature heat to the high temperature heat without producing uh, any external work output. Okay, without disturbing the surroundings, without producing no other effect. So this is a clear cut violation of the Clausius statement. Okay, so you can see that if any part of the system is violating Kelvin Planck, then it is quite obvious that it will also violate the Clausius statement also. Okay, so by this understanding, we can say that uh, if if there is a chance that uh, so it is quite obvious that whenever you will see that a part of the system is violating the Clausius statement, it is obviously going to uh, violate the Kelvin Planck statement. And in either words, the opposite also is true. So from today's session, we have understood that heat is a low grade energy, whereas work is a high grade energy. So there are some unique processes which can occur in a single possible direction only. Okay, so this type of processes can be spontaneous as well as they can be performed with the help of external aid. Okay, now there are some spontaneous processes which can also occur in the reverse direction, but in that case you need some external agency. And there are some specific processes which can occur in both the directions, but in that case, even if the system returns back to its original position, the initial position, the surroundings are permanently damaged. They are permanently disturbed. Their thermodynamic characteristics are permanently disturbed. Okay. So with this, we have discussed how does a heat engine work, what are the method to calculate the efficiency of a heat engine, and how does heat pump or refrigerators work, what are the methods to evaluate the performances of heat pumps and the refrigerators. And we have seen the two famous statements, the Kelvin Planck statement and the Clausius statement, and we have found that these two statements doesn't differ from them. They are actually they are equivalent to each other. So this was the discussion regarding this class. In the next class, we'll see what do we mean by irreversibilities, what do we mean by irreversible and irreversible process. We will discuss the reversible process also, and with that understanding we will move on to the concepts of Carnot's theorem, Carnot's engine, and other things. Okay, so for today let us end it here. Goodbye, and thank you all for your time.